Okay, I know that was a very long, difficult example. Um, and I know it was probably hard to follow because this is a very new idea for us, but I really don't think Stokes' theorem makes sense as a list of steps until you've seen all the different choices you have to make. So now that you're aware of kind of the potential issues in this problem, let's talk through the steps that you'll follow to solve a Stokes' theorem problem in general. So kind of the first challenge you're going to have is that you want to identify Stokes is appropriate. So generally the things that are going to have to be true is that you're computing line integral problem for closed curve. You're going to want del cross f is not 0. So there's no potential function for this type of vector for which you're computing the line integral. Once you're sure about that, you're going to have to identify your vector field f. That should be the thing inside your line integral equation. Sometimes it won't look like a vector and you have to pick it out the way that we did in our example. And the reason you have to identify that f is because you're going to have to compute the curl of that vector field. These steps you can really do in any order you want. That's just usually an easy thing that if you expect to get lost in the rest of it, doing this early on will at least get you partial credit. And then you're going to want to identify the curve C and its corresponding surface. So your curve will be closed. And your surface S will potentially have more than one way you could pick it. So my advice here would be to look for simple shapes or functions z equal to a bunch of stuff. So in the context of the example we did early on, we found our C and then we had to pick our surface S, and we picked this flat disk that's a simple shape that corresponded to a simple function z equal 1 minus x. Either the visual or the function would have clued you into this is a good surface to use. This one maybe is not so good. It's a complicated function. The shape is complicated. You wouldn't like it as much. Once you've identified your surface S, you're going to want to write z equal to f, a function of x and y, for surface S. So just solve for z on one side, everything else on the other. The reason for that is because you need to compute ds equal to the root fx squared plus fy squared plus 1. And then you need to compute your normal vector minus fx minus fy, 1 over the square root of minus fx squared minus fy squared plus 1. So the reason why we're doing this kind of unnecessary thing where you normalize n and have it in the ds is because there's always an option that s is going to be a flat thing. So for example, z equals 1, x equals 2, etc. Then your normal vector, you're going to be able to pick out pretty easily. It could be like 0, 0, 1 or 1, 0, 0. And you just need to make sure that these are unit vectors. So don't do like 0, 0, 2 or something. The formula would still work for the z one. Okay, so we've got our n, we've got our ds. And then you're going to need to identify your region R for the surface S. Which that's just going to be calling back our surface integral section 13.5 for how to do that. And then after that, I think we've got all the pieces. Your line integral over the closed curve C is going to be the double integral over the region R of your del cross F dotted with N times ds. And then you just evaluate. And remember, with all these problems where we have to convert a complicated integral back into 2D integral or 1D integral that we know how to solve, you can always go back and use previous methods to make that easier. So if you write a double integral in terms of dy dx, but think it's easier to solve in polar, do that. Don't lock yourself into anything that's going to be more challenging than it has to be. Are we doing okay on time? Great. So at this point, because these problems take so long to solve, you'd be asking yourself, like, why would I use Stokes or when would I use it? And I tried here to kind of write out when Stokes would be appropriate, but I really want to think about this in the context of you have a general line integral problem. How do you choose what to do? So given a line integral problem previously, you would have had kind of two options. So you could have parameterized C with some kind of vector, and then you would have converted it into a 1D integral f dot r prime dt. Or you would have found the potential function so that your vector was actually a gradient. And then you would have used the fundamental theorem. Your line integral is actually just f at the endpoint minus f at the starting point. So those are the two old ways that you knew how to compute line integrals. And what we've done here is we've introduced a third way where we use Stokes to convert to a surface integral. of the curl. Okay. So those are the three different ways that you can solve line integrals. And Stokes has real clear rules. You need C to be closed in order for this formula to work. The second thing I said, that del cross F shouldn't be equal to 0, wasn't really a rule of Stokes. And you technically can use Stokes if del cross F equals 0, but you would do all this setup to integrate 0 and get 0 out of it. And the reason for that is because if del cross F equals 0, that's when you could find a potential function. And you might have noticed before, if your endpoint and starting point are the same for a potential function fundamental theorem type line integral problem, then this difference is 0. And so if del cross F equals 0 and you try to use Stokes' theorem, you'll get 0. If del cross F equals 0 and you have a closed curve for the fundamental theorem, you'll get 0. Those are the same outcomes of doing a silly thing to get 0. So you would use the fundamental theorem when del cross F equals 0 for a curve that isn't closed, because if it is closed, you would just get 0 out of this process. And that's why I say you should only use Stokes' theorem when del cross F isn't 0 if you can't find a potential function, because potential functions are easier. And so this parameterization is kind of going to work all the time. I think you should only use it if you can't do potential functions because it's a bit longer. You need to be able to parameterize your curve. So it's kind of a catch-all. Maybe even if you have a closed curve, if it's been parameterized for you, you might prefer to use the old method still, and that's okay. Really, the takeaway here is going to always be to pick the easiest or fastest way to solve an integral. And I just hope seeing those three options side by side help you see where Stokes fits into that.